Welcome to Symposium 3. The theme of this session is Progressive Textile. The presentations will include Sustainable Textile Technologies, Textile Engineering, Technical Textiles and Composites, Textiles of the Future.
Okay, honor for me to give a presentation today. Well, my topic is effects of weaving structures on the water wicking evaporating behavior of woven fabrics. My presentation will be divided into these 4 parts. Firstly, I'd like to briefly introduce the research background. As you know, thermal comfort is one of the most important properties of textiles, and it depends heavily on heat and moisture transfer capability. Well, to provide a cooler and drier feeling in hot and wet environment, water transfer is very crucial for human beings, especially in some special working condition. And there are 2 sequential processes during water transfer in textiles. One is synchronous wicking evaporating. Another one is evaporating alone. In case of excessive perspiration, clothes are saturated with air and moisture. The relatively slow action of wicking and evaporating could make people feel discomfort. So, evaluation of the water transport ability of textiles is very important in fabric design and some functional clothing. So the main purpose of this study is to provide an in-depth understanding of water transferring in woven fabrics. As we know, fabric porosity can influence moisture transfer, and it was found that the float and interlacing point, which are the 2 elements in a weave, can increase the whole water transfer to a certain level. However, studies on water transfer behavior of woven structures, considering percentage influence of different weaving elements, are very rare. So in this study, we designed 4 types of basic units in 1-layer woven fabric, depending on the 2 directions of yarns, interlacing or non-interlacing. So in this study, we aimed to review the water transfer process of woven fabric and to identify its main influencing structural parameters. Next, I'd like to show the experiment design in the study. All weave types are composed of interlacing points and non-interlacing points, as I just showed here. So in the study, we adjusted the proportions of the 4 units in a weave and create different structures with varied floats. Since the weave pattern influences wicking and evaporating behavior of fabrics, so the 4 weave units and their arrangement. Its fabrics were designed and produced with different proportions of weave units. And you can see these 8 fabrics are with different weave units and different arrangement of these units. Well, 2 parameters were defined here to account for the number of floats in a weave. One is CFF, it's short for crossing over firmness factor, and this is a way to calculate it. Well, FYF is short for floating yarn factor, and it was calculated based on this formula. And all the calculations are listed on the right table, in the right table, in the table on the right. Well, to test these samples, firstly, we characterized all their physical and structural properties of these 8 woven fabrics. Area density thicknesses were measured according to testing standards, and the other properties were calculated. And here are the results of this basic physical and structural properties of these samples. In addition to physical and structural properties, we focused on weakening evaporating behavior. So we must have a better way to evaluate it or collect the data of these measurements. So in the study, we designed an instrument to detect weight loss. You can see on the left, you can see in the figure on the left, this is the diagram of this instrument. It composed of an electronic balance, liquid reservoir, iron holder, and a clamp to add pretension to the samples. And the test procedures are shown here. First, we immerse samples into liquid with 20 millimeters, and then record weight loss every 1 minute in phase 1 and every 10 minutes in phase 2. And then all the measurements were repeated 3 times. This figure, you can see it has 2 phases. This illustrates the weakening evaporating process, and the curve is divided into 2 parts. In phase 1, steady weakening and evaporating in the first initial with 1 water transfer speed. Well, in phase 2, steady weakening evaporating from 10 minutes to 120 minutes with another water transfer speed. So we used this instrument and collected the measurements of weakening evaporating behavior. After analyzing the data, we draw this picture to show the weight loss versus the time. According to a statistical analysis, the moisture transfer speeds of the 8 samples were significantly different in phase 1. It can be observed from the figure that their overall behavior followed the same trend. Each of the 8 samples reached their crucial points in phase 1. And the water transfer speed finally had a dynamic balanced value after achieving the longest weakening distance. Now in phase 2, the NOVA results indicated that the wave pattern has no significant influence on the transfer speed. Well, the figure on the right shows the water transferring speed versus the sample. And the transfer speed in phase 1 and the total transferring speed shared a similar chain and varied significantly among 8 samples due to the large contribution of weakening to water transfer in phase 1, and the total water transfer speeds are significantly different among the samples. And this suggests that weakening dominates the whole water transfer process in the vertical weakening evaporating test. Additionally, in this figure, we can see that these characters could be divided into 2 groups. Group one includes sample 1, 2, 3, 4, 5. And their floats are distributed evenly throughout the entire fabric surface. While group 2 includes vertical stripped fabrics from sample 6 to sample 8. And their total water transfer speeds are higher than that of group 1. So you can see the difference between the two groups. What's more, in the study, we also use correlation analysis to evaluate the strength of the association between total water transferring speed and the investigated variables. And their results are listed in this table. Among all the variables, we can see that these three variables, that's FYF, which is floating young factor, had the largest correlation, and followed by CFF and proportion of unit 1. This means that total water transfer speed has a strong association with the wave. Well, in addition, it is certain that the wave parameters themselves have a large correlation value. And it should be noted that fog porosity has the highest absolute correlation coefficient. You can see here the fog porosity has higher correlation coefficient with the CFF and FYF. This is considered that the bulk porosity depends markedly on the wave parameters. So increase of the line's floating point property by varying wave parameters can create a looser structure with more micropoles. So in this case, air convection between the surroundings and the fabric inside could be enhanced, which helps air to make the free vapor out and accelerate evaporation. Finally, to avoid disturbance by multicollinearity among variables, we performed a principal component analysis on the data. The first two components, PC1 and PC2, out of 6 obtained principal components, were selected as the new variables to build a regression model because these two components counted for 94% of the relevant information. Well, in this figure, we can see that principal component 1 is mainly composed of unit 1 and unit 4. And we know unit 1 is made of the 4 points are interlaced, while unit 4 are not interlaced, which means they're all floats. So unit 1 represents the tightest structure, while unit 4 represents the lowest wave structure. While principal component 2 is mainly composed of unit 2 and unit 3. The proportions of the 4 units of wave explains most of the structural variable of the fabric and can prove that unit 1 and unit 2 are two main factors influencing the structure and performance of the fabric. Finally, based on the principal component analysis method discussed above, a valid regression model was established. In this figure, the scatter plot and the regression plane of the principal components versus total water transfer speed are plotted. While in the linear regression model, the coefficient of determination of the of two principal components is smaller than that of three principal components. So in the end, the linear regression model was built with three components, and the equation is showed here. Now we can use this model to predict the total water transfer speed. I'll make a conclusion. In the study, a wicking evaporating test based on vertical wicking was used to investigate the water transfer behavior of cotton woven fabrics with different waves. And there are two phases during the wicking evaporating processes. In phase 1, it's unsteady wicking and evaporating. And in phase 2, it's steady wicking evaporating due to equilibriums between the capillary and the gravity forces. Because of the uneven degree of capillary channels induced by different structures, the water transfer speed in phase 1 varied with samples. However, it was constant regardless of woven structures in phase 2 because of the screening phenomenon induced by continuous saturated conditions. The water transfer rate from a fully wet fabric surface is basically identical to that from a free liquid surface. Also, in the study, we can see that woven fabric with more float have more micropoles, processing non-uniform capillary channels and more airspace for evaporating. Float can increase the total water transfer in the wicking evaporating process more than interlacing points. Generally, findings in the study provide an in-depth understanding about effects of weaving design on fabrics, wicking evaporating behavior. And in the further study, more wave structures should be considered to investigate effects of the structural and wave parameters on the water transfer. That's all my report. Thank you for your listening.
I finished my presentation. Does anyone have a question for me?
Thanks very much for your presentation. Then I think I can ask the listeners if they have any questions for your presentation. Any questions? Maybe if there are no questions, then maybe it means that your presentation was very clear. But maybe if there are questions we can raise at some point later on in time. Thank you very much.
Okay, thank you.
Do we have Dr. Mohammed Amin ready?
Yes, I am. Good morning.
Okay. So your session is on carbon nanotube film stroke Bdms composite towards functional actuator.
Exactly.
Can you please present?
Yeah, definitely. I made a video and it's on screen right now. Can you see it?
Yeah, we can see your presentation. Go ahead.
Okay, thank you so much. Dear Chairman, honorable guests and CITA committee, it's a great
pleasure to be here with you today to talk about my last work in Northwest University. I'm in Aurora from Morocco, and I'm doing my PhD under the supervision of Professor Yipi Chu and Professor Fuji Xu. In today's presentation, I will present carbon nanotube film and Bdms composite word multifunctional actuator. So carbon nanotube is known as graphite sheet rolled into cylindrical shape, and it's mainly composed with carbon atoms banded together into a diamond shape. Many varieties of carbon nanotubes are produced, such as single-walled carbon nanotube, which is made by a single cylinder of carbon atoms. We also find double or multi-walled carbon nanotubes according to the number of external and internal walls. The CNT can also be attached in a random or aligned way to form a CNT bands. Depending on the process used, we can fabricate high aligned CNTs such as arc discharge, laser ablation, but those methods are time-consuming and expensive. In our work, we use floating catalysts, chemical vapor deposition method, which is the most effective process to produce and assemble CNT into a micro scale. The produced CNT are like film or bucket paper and could be turned into yarn or rope, or directly used as a film according to the application needed. As produced carbon nanotube film by floating catalyst vapor deposition method is a condensed entanglement of carbon fiber as shown in the SCN picture. The material is mainly fabricated with carbon atoms, as shown from the FTIR and XPS results. In addition, the carbon nanotube film has good mechanical properties with a tensile strength of around 140 megapascals and a strain of around 20%. Also, the carbon nanotube film can stand high temperature till 480 degrees before total degradation in air, as shown from the TGA curve. In addition to be strong and lightweight, the produced CNT could be fused as e-heating material. The carbon nanotube film is able to convert the electrical energy into heat as shown in the figure. We adhere to the standard CNT film, copper wires, and studied its e-heating performance. The CNT film can generate heat even after several deformations such as bending, knotting, and twisting, and can reach its steady state temperature almost instantly at the moment we input the power. We reach high temperature systematically. Here is the 2D profile of heat distribution on CNT film surface, which shows an even distribution of heat on CNT film. In comparison with other material made so far, such as e-heating 7 nanowires composites and graphene, the proposed CNT film can generate high temperature within few seconds and low voltage of 2.5 volts. As application of the thermal conversion of CNT film, we have made a composite based on CNT film and Bdms to make an electrothermal actuator. First of all, we have coated CNT film with different thickness of Bdms layer and cut it into specific shape as shown in this figure. Finally, we soldered copper wires to both edges of the U-shaped composites, and we applied direct current to activate actuation. Due to the porous structure of CNT film, the Bdms polymer penetrates and adhere well to the CNT surface as shown in the SCN figure. From the FDIR test, new silicon groups appears on the composite, which was formed mainly from the Bdms polymer. In addition, the TGA test demonstrated that Bdms starts degradation after 300 degrees before totally degrades after 500 degrees, which demonstrates the limits of the fabricated composite. Due to the high thermal conversion of CNT film, the heat is transferred directly to the Bdms, which expand under heat and lead to mechanical deformation and bending of the composites as shown from the optical and thermal images. The mechanical movement is mainly due to the coefficient thermal expansion mismatch between carbon nanotube film and Bdms. Among common polymer, the used Bdms has a great coefficient of thermal expansion and is a soft material which leads to a large deformation. In our study, we have plotted CNT film with different Bdms thickness and studied its effect on the mechanical bending behavior according to the different applied voltages. As we increase the voltage, the resulting bending angle of the actuator increases systematically, and the converted temperature increased simultaneously too, as shown in this figure. However, Bdms with a thickness of 1.5 showed large deformation corresponding to the optimum amount of the polymer to get optimum actuation for the designed actuator. In time, the actuator of 1.5 mm in thickness reached its bending states within 17 seconds and remained stable before cutting off the currents and returned to its initial states within 10 seconds. The bending angles also increased with the voltage from 50 degrees to 200 degrees as the temperatures increase and the applied voltage of 4 to 7 volts. In addition, the fabricated Bdms actuators showed a stable response in time with a stable bending angles of around 100 degrees and 6 volts, even after 20 cycles of on-off. And the bending time and recovery time keeps also stable after 20 cycles. Finally, ATA actuator shows great strength and can hold around 1.53 its weight and lift around 5 times its weight as shown from these optical images. We also studied the actuation behavior of the fabricated CNT film Bdms actuator by dipping it into water and freezing it as shown in this figure. We applied a voltage of 8 volts to activate the actuator in these circumstances, and after 20 seconds the ice starts melting and the actuator starts to bend after 25 seconds as shown in the figure, with the increment of temperature, which demonstrate the wide utility of the proposed and fabricated actuator. So thank you very much for your attention. Please, if you have any questions, feel free to contact me by email, WhatsApp, or chat, as shown on the slide. Thank you again for CETA Committee, Moi University and Northwood University Textile College for their tremendous effort to make this event happen in this worldwide hard circumstance. God bless everyone.
Thank you very much, Dr. Amin.
Thank you.
I would ask if there is any question for the presenter. If there is any question for the presenter, maybe you can show by a lifting of the hand, or you give a comment. Okay. Apparently, we don't have a question, and we might come back to the presenter. I am asking if the next presenter, Cosmas K. Kosgei, is available and ready. Hello?
Hello, Professor Zhang Kun is not available now. So we find someone to play his presentation recording. Is that okay?
That's okay?
Yes, we found someone to play his recording now.
Okay, let me, okay. Yuan Jen, you are ready for presentation? Hello? Hello?
Hello?
Who is ready for presentation? We have...
Okay, please speak. Professor Zhang Kun prepare his recording here, and now I think we should play his recording as the list. Is that okay, Professor?
That's okay.
So today I'm going to talking about the design and manufacturing of thermoelectric textiles for harvesting thermal energy for and how to power the electronics. And we're going to talk about how we fabricate the segmented thermoelectric yarn, and also we investigate the effect of textile structure, and we demonstrate how the thermoelectric textile can generate some power and power some electronics. And also finally, we demonstrate how to use the industrial textile process to scalable fabricate thermoelectric textile. All right. So as we know that for the Internet of Things, most of the wearable electronics consume only 1 to 10 milliwatts power. And thermoelectric materials involve the conversion between the heat and electricity. So in this diagram, showing that if you apply a temperature difference or gradient between the top surface and the bottom surface, you can generate power or the potential. If you connect with the electronics, they can generate the current or the electricity. And inverses, if you apply current into this thermoelectric generator, you can generate the temperature difference between the top and the bottom surface. If you can dissipate heat very quickly on the hotter side, then you can keep the cold side with a very stable temperature. Then you can use this generator as a solid state cooler. All right, so there's no need to be charged, and also it's very safe, and no mechanical process. You have no noise, and the thermoelectric properties of the materials mainly dominated by this equation. And the ZT, if you have high ZT, you can have high performance with the cooling effect or the power generation. And the ZT is dominated by other three key parameters like the speed coefficient, the sigma, electric conductivity, and the conductivity. So typically, people want to have a high power factor, means the highest Seebeck square times electric conductivity. And also, we want the thermal conductivity lower. But there are two different conflicts. If you have a high Seebeck, you gotta have a lower conductivity. If you have high conductivity, you gotta have a lower thermal conductivity, high thermal conductivity. All right. So basically, there are two types of thermoelectric generators. Like first, the thin film based. So in this type of thermoelectric generator, so it is made by coating the printing thermoelectric materials on the plastic substrates. The fabrication is very simple and relatively easy to control the properties. However, the electricity is generated in the plane direction, which is not actually good for practical application since the temperature gradient is usually vertical to the heat source of human body. Like if you apply, for example, if you apply a thermoelectric generator on your body or your human skin, the temperature gradient may it is vertical to your skin, right? So this structure configuration is not practical. And the initial concept of the thermoelectric textile has a very similar configuration as to that of conventional thermoelectric generators. Like in this diagram, we have p-type materials and n-type materials. We have them electrically connected in series, and we have them thermally connected in parallel. So this is the basic structure of thermoelectric generator. And also the 3D deformable thermoelectric textile has a similar configuration. We have n-type, p-type, ultimately, woven in the fabric in the thickness direction, so we can have a kind of similar configuration. And the current design of the power generation of the thermoelectric textile is performed in the outer plane direction or in the thickness direction, and can be practical. And the current design is very complex, and not a lot of people focus on the manufacturing process, and nobody understands the textile structure effect of the thermoelectric power generation. So the first step, we fabricate the segmented thermoelectric yarn by using highly conductive cumulative yarn. We wrap them into PET plastic plate and then coat them with silver paste as the interface with the p-type materials and n-type materials, and we use the center part as the electrodes. So first we drop that into a ink with the p-type paste. P-type paste is kind of conducting polymer with the p-type properties, and then we dry it and flip over and soak another side into the PEI solution. PEI solution can drop the carbon tube into the n-type. And finally, we try that if we unwrap the carbon yarn, we can have this segmented structure. You have alternatively p-type, n-type, p-type, n-type. So then we can use the thermoelectric segmented yarn to fabricate the thermoelectric generator. And we confirm the doping of PWPSS and PEI by EDS mapping. As sulfur element is a characteristic element in PWPSS, we can see that it is evenly coated. And for the PEI, it has a characteristic element nitrogen, so we can see that also they are very evenly distributed along the cumulative yarn. Okay, the middle part is the pure cumulative as the electrodes connecting the p-type and n-type materials. All right. So we also measure the thermal properties of the different three segments, like the connecting polymer, pure connecting cumulative yarn and p-type one and n-type one. We find that the power factor of the pure one is about 240, and for the p-type one is about 500, and for the PEI one we have 660. This is also kind of the highest one reported, and we confirm the n-type doping by PEI to using the UPS measurement. We can see that Fermi level move upwards to closer to the conduction band edge, and this is a very typical phenomenon for n-type doping. Typically, n-type materials has very closed distance for the energy, formula energy to the conduction band edge. And for highly doped N-type materials, you have formula level inside the conduction band. And we then investigate the effect of the textile structure on the power generation, and we select the 3 types of fabrics, like the knitted fabric, and the spacer fabric, and the woven fabric. And we use a finite element analysis to simulate the power generation. And this is the main result. You can see that the bare single PM pair of thermoelectric yarn. It can only generate a very small temperature difference. Then you can have only very small potential, the voltage difference. But for three types of fabric, you can significantly enlarge the temperature difference between the top and the bottom surface of the thermal generator. And also we can see that knitted fabric shows the highest temperature difference among all 3 types of fabrics, and corresponding highest potential generated. And also we can see the spacer fabric showing this very close properties, performance to that of a knitted fabric. All right, so we believe this is caused by thermal transporting the fabrics, and the total temperature difference between the thickness direction is dominated by the total thermal resistance. And we know that the different fabric configurations result in different thermal resistance of textile, and thus making the temperature distribution and the corresponding potential distribution change within the thermoelectric yarn. So typically, the woven fabric usually have very regular yarn arrangement in the thickness direction. So we can believe that there are few closed channels that can look like static air to express the thermal convection in the woven fabric. And though the knitting loops are predictably connected with each other, the wet knitted fabric or warp knitted spacer fabric usually have an irregular yarn arrangement overall. Thus, they may lock more static air for reduced thermal convection in these fabrics. So clearly, seeing from this summarized the simulation data for different models, we can see the knitted and spacer fabric share the best performance of the same specific weight and thickness, and with comprehensive consideration of the fabric structure, effect, and difficulty in practical fabrication, we prepare a warp knitted spacer fabric shaped thermoelectric textile. And the experimental result is kind of slightly lower than that of the simulation result. As mentioned before, the actual structure of the thermoelectric generator, the textile-based ones, share a similar configuration to conventional bulk organic thermoelectric generator. And the thermoelectric textile showing very flexible properties and the bending, twisting, compression, and the performance is kind of stable even after 1,000 cycles of bending, twisting, and compressing. Moreover, it shows excellent flexibility and functional stability and liquid nitrogen temperature, which lithium-ion battery will disable due to the frozen ion transport. And we then measure the power generation and the different temperature differences and external resistance. We get the high power density of around 51 milliwatts per square meter and the temperature difference of 47 kelvins. With the voltage density is about 520 watts per square meter, and we can generate 3.7 watts. So this is comparable to that of lithium-ion battery. And our performance, our thermoelectric textile outperforms the majority of textile-based thermoelectric generators, and it is the best one ever reported among organically based thermoelectric textiles. We further demonstrate the capability of powering electronics for practical applications by firstly charging a supercapacitor. Then we use the supercapacitor to power the electronics, and the full diagram shows how we charge and discharge the supercapacitor. And we can see that we know the red part for the charging time and blue type, sorry, the green time showing the discharging time. We can see the charging time is much shorter than that of the discharging time in the consumer product. So that means that we can use the thermoelectric textile to continuously power electronics. All right. So this summarizes all the power requirement for different electronics, and we can see that this is much lower than that of the power generated from the thermoelectric textile. And this video shows how we apply a temperature difference by liquid nitrogen, and then how we generate the power to power something. And also we can use the thermoelectric textile to directly power the electronics like the thermometer, hygrometer, and the UV director, and the pedometer. And finally, we demonstrate how to scalably fabricate the thermoelectric textile by electrical textile process. For example, we quickly braid the thermoelectric yarn with a shear of polyester to improve the anti-friction properties, and then we use the computerized CNC machine to execute the thermoelectric textile. So finally, and the textile thermoelectric is very flexible. And it should be mentioned here that we can precisely control the T-type and type movements in the typical machine. So the T-type item can maybe not that range all the time very good in the textile. But in the lab project, we do that with unity. All right. So finally, I would like to conclude my presentation, and we demonstrate thermoelectric textile, and we investigate the effect of textile structure on the power generation, and also we have a high power generation performance with the power density around 50 milliwatts per square meter. The different temperature difference around 47 kelvins. And we, for the first time, successfully and continuously power some variable electronics using thermoelectric textile. And finally, I would like to thank one group and thank some collaborators and also financial support. Thank you very much for your attention. And if you have any question, you can ask me via phone call or email. Thank you very much again.
Hello?
Hello, I think it's finished.
Professor Kunjang, you're finished?
No, I'm not Professor Kunjang. I'm his student. I just
okay, all right.
Yes.
Okay, now
Sorry.
I will ask the listeners if you have any question on the presentation on the design and manufacturing of thermoelectric textiles for harvesting thermal energy. Any question? I don't seem to see any. We had a presenter, Professor Liva van Langenhoff, who was supposed to give us a keynote speech at the beginning of the session. I can see she has just arrived. Can we give her time? Professor, are you ready to give your keynote speech?
Yes, Eric, I'm ready.
Okay, thank you very much. Please welcome and give us your keynote speech for today.
Okay, thank you. I will share my presentation. Just 1 minute. Can you see my presentation?
Yes, we can see it. Please go ahead.
Okay. So today I will give some overview on the energy supply in smart textiles and the work that we have been doing on this topic. And some of this work has been done together with Moy University, and it has led to several PhDs. So first of all, well, just a brief introduction. Smart textiles are complex systems. They have different functionalities. They measure, they process data, they respond, they communicate, but they need, to do this, they need some power, some electricity, and all of this has to be connected, integrated, and has to be able to function as proper textiles, meaning without harming the comfort and surviving regular textile processes such as laundry and multiple deformation. So that's the challenge we are facing. Now our research mainly contains 4 steps. First, conceptual design. So we look at the different concepts that have been described in literature, in textiles, but also in other areas. And from that, based on that, we pick solutions, concepts, which are compatible in terms of the materials used and also the processes needed for manufacturing them. We also look at modeling and simulation because this allows us to optimize the design and the materials choice before making anything. Then, of course, we have the fabrication, which, as I said, should be as much as possible in line with existing textile processes in order to avoid large investments in new facilities. And then, of course, also the testing. Now, some products are already on the market. Here are just some examples. Mainstream markets, such as the Adidas My Coach shirt, which is used for heart rate monitoring for sports people. Then the mid-segment is fashion. This is an example of a cute circuit. It's a t-shirt equipped with LEDs and movement sensors, accelerometers, which monitor when a person is moving, and then the movements are reflected in the lighting of the LEDs. Then we also have an example for elderly people. It are carpet tiles that can be put together in a room, and the system will organize itself in order to create a profile for the room. And it has pressure sensors, so it can monitor which tiles are subject to pressure, how big the pressure is, and what is the pattern. And based on this, you can find out where a person is walking, and also whether a person has fallen, for instance, and might be in need for help. And then we have the Firefighter Suit, which is very high end. It monitors the person, the body, the activities of the person, and also the context, so the overall situation. Now, all of these have several functions, and as a function of the elements that are part of the system, we may have different needs for energy. So we may need a power of microwatts for simple sensors, up to watts when we speak about heating, cooling, lighting, things like that. We look at centralized versus distributed systems. So we may have energy supply on a local base, or we may have a central system from which the energy is then led to the various parts. We already heard some presentations before regarding storing energy, batteries, and also generating energy, which is actually scavenging energy and transforming it into electricity. Both of them are feasible in textiles, but yeah, we have to make a smart selection and combine them. And as I said, they have to be comfortable, mechanically stable, and washable. The first work we did on energy storage has been in collaboration with Moi University, and it's Dr. Sheila Odiambo who did this work, and it was continued by Dr. Ida Nuramdani from Indonesia. And actually it consists of two wires which are conducting, and they act as the electrodes, so a positive and a negative one. And it turned out that adding a third neutral conductive yarn helps improving the performance of the battery. We used P.PSS as an active material, which is a conductive material. You can see the composition here in the slide, and we used it as a coating. So you can see the upper view as well as a cross section, where you can see the conductive yarns that act as an electrode, and the coating itself on the fabric. Now, here in this slide, we mentioned stainless steel as conductive yarn, but we also looked at silver and copper yarns, and it turned out that this is having an impact. So every element has an impact, but it gives you an idea also on the size of a battery. So it's really small. It's 1/4 up to half square centimeter. Here you can see the performance of the battery and a picture of the battery. So it's really small, approximately 5 by 5 millimeters. And here you can see how it performs as a battery. This figure B shows that it's a combination of a capacitive and an electrochemical battery. The capacitive battery has the disadvantage of having a variable voltage, but it has the advantage of being much faster. So it can deliver energy much faster as an electrochemical one, and the charging is also much faster. An electrochemical battery has a constant voltage, but it is rather slow. It can be integrated in a textile, for instance, by weaving, by inserting the conductive yarns by weaving, and then the P-dot can be applied by printing. At the end of the research, we managed to power a small calculator, so a simple traditional calculator, during approximately 1 minute, and this for a battery of 5 by 5 millimeters, so 25 square millimeters. And this shows that actually you can provide quite a large power capacity when you would exploit the full surface of the textile. At the end of the research, had to be improved the washability, and this charge, the system is subject to spontaneous discharge, which is due to the conductivity of the P.PSS. So we will try to solve this by reducing the conductivity of the P-dot. And also washability, this can be improved by coating the P.PSS, but of course, when we go to larger surfaces, this is not what we want to do, because then this changes the thermal comfort of the textile materials. Here is an overview for energy scavenging of different principles and just some indicative values that of power that can be reached. photovoltaic for sure is one of the better materials in terms of output power. Outdoor, we can reach 20 to 100 milliwatts per square centimeter. Indoor, this is around 1,000 times less. Piezoelectric shoe inserts, for instance, has reported power output of 330 microwatts per square centimeter. Electrogeneration, 1 milliwatt. It's difficult to express this as per square unit square. Temperature gradient, we just listened to a presentation just before this. Body heat is reported to have an output of around 25 microwatts per square centimeter. But of course here the temperature difference is much lower than what has been reported in the previous presentation. And there they spoke about a temperature difference of between 40 and 50 Kelvin, whereas body heat would be, when you use body heat, this would be around 10 Kelvin. And then also antennas from electromagnetic fields, around 1 milliwatt per square centimeter. But important to remember that energy scavenging always comes at a cost. For scavenging light, for instance, then you have a dark textile, which because it's absorbing the light, that's exactly what it wants to do, which may be inconvenient for textiles. Piezoelectric, you can feel that the resistance of using the textile is a little bit higher. It may be very, very low. A shoe insert, for instance, you won't feel because it will be way below the energy you need for bending the shoe, for instance. And an antenna, if you would scavenge all the electromagnetic energy in a room, then none of our mobile phones would still be operational, and also the Wi-Fi signal would be completely absorbed. And so this is something we must be aware of. This is an example. It's not from us. It's from colleagues from Eastern Europe. They have created an electrode generator. So they have used the principle of electromagnetic induction. They have inserted a magnet in the sleeve and a coil in the pocket of the vest. And as you walk, you swing your arm, and the magnet, with every swing, the magnet will pass by the coil and induce an electrical current. So here also you won't feel this, but if you would move to very extreme cases, you would really feel that your arm has difficulties passing by the pocket, and it would take you some additional energy to pass there. Here you can see, an example of the power that can be generated. So you can see it's around 100. It's of the order of a few hundred of microwatts for this configuration with the dimensions that you can see here. So just 10 millimeter around 1 centimeter. Energy from motion, piezoelectric materials. Here the concept we have chosen would be a conductive core, then a piezoelectric layer, and then a second electrode around it. And if you bend this material, or if you stretch it, this would give rise to an electrical voltage. Challenges here are the materials. The concept, this is one concept, a fiber, but it could also be a coating. And then the production, mainly the poling. Now in the next slide, this is a theoretical consideration that shows how important minimum thickness is. This equation is kind of an extension of Hooke's law, whereby you find a relation between the deformation and the force, Now, in this case, for piezoelectric materials, a term is added to this equation, which adds a force needed for the molecular displacement of the active groups in the molecule. Now, when you deform a material, the piezoelectric effect is a surface effect. So the energy you need for deforming the inside, the bulk of the material, is actually wasted. Part of it will be recycled, but as you know, deformation for most materials is not fully elastic. It has some hysteresis, and this is a loss of energy. So, and for a thick material, of course, this energy will be higher, this energy loss, whereas the piezoelectric effect is purely surface. So the bulk material doesn't add to any additional power. That's why we need a minimum thickness, but the minimum should not be too low, because then we may have percolation of current between the two electrodes, and then you get holes and the system is broken, it doesn't work anymore. And particularly during the poling, where we need a high electrical field, this is an issue. Energy scavenging from radio frequency waves, so electromagnetic waves, is also a possibility. This is the work of Carla Hertler and Abdul Wahab Menon, who is still working on his PhD at this moment. There are two approaches. One is induction. This is one of the mechanisms we used in the very first research in this area around 20 years ago, whereby we needed, we were powering a baby suit for a baby that was a newborn baby that was lying on his or her back in a baby bed, and for monitoring respiration and heart rate as a way to prevent sudden infant death syndrome. And so with this coil, it's comparable. I don't know whether you also have them in Kenya, but here it's quite popular to have inductive charging of toothbrushes, for instance. You just put your toothbrush on a holder and it will automatically charge. So what you need for this is parallel surfaces and a short distance, which is available when a baby is lying in a bed on the back. Then you have the back of the baby suit for one part of the antenna, and the other one can be inserted in the mattress. Once the baby starts moving, for instance, this is not working anymore, because the surfaces will not be parallel anymore, as the baby will turn around, and then we have to go to another way, and then we can use an antenna, a regular antenna. This is the green patch you can see here, but actually the green patch is the substrate. The antenna is the gray part, which is laminated in this picture. Now, how does simulation support design? In antenna, it's all about bandwidth, and bandwidth in the upper left picture, you can see here the bandwidth of an antenna. So as a function of frequency, the energy captured by the antenna will vary. And you can see a peak here around 2.45 gigahertz. And the bandwidth is then defined as the frequency range whereby the losses are less than minus 10 dB. So in this picture, you can see the bandwidth of this particular antenna. You see two lines here, on body and off body. So when the antenna is worn, the bandwidth goes down a little bit, because the body is absorbing part of the energy. In the upper right picture, you can see the emission profile of the antenna. so in the different directions. And of course, we want an antenna to emit homogeneously in all directions, not to have any preferential directions, and also to have no emission backwards, because this is then absorbed by the body. In the lower right picture, you can see the calculated profile of different dimensions of antennas, so different sizes. And you can also see that there are two peaks here, and the second peak is caused by the presence of the hole in the middle of the antenna. In the lower left picture, you see an antenna and it has a hole in the middle. By inserting a hole, we can drastically broaden the bandwidth. And this is something that you can clearly find by running the simulations. So this is how the simulation is really helpful for creating good antennas. The fabrication was by embroidery, lamination, and printing, and the testing is done in an anechoic room, of which you can see a picture here. It has no specific textile requirements. Well, the standards have no specific textile requirements because a standard antenna, a common antenna, doesn't have any textile characteristics. So there are no prescriptions regarding the clamping or the room conditions, temperature, humidity, etc. And also the number of repetitions is not mentioned because the variability of a standard antenna, a common antenna, is way less. But for textiles, this is really important to take it up in the research. Then we also do some work on thermoelectricity. It has been explained already in the previous paper, so I won't repeat this. The start of the work has been the thermocouple with copper and nickel materials. The PhD student working on it is Hardianto, and he will defend his PhD next week. So should anybody be interested in joining the presentation, please send me a message and I can forward you the link. It will be online. So the concept we have chosen is a wire which is coated in dedicated intermittent areas with a second metal. So we have a conductive core coated with a coating at regular places, as you can see here. How it is inserted in the fabric and how it is produced. The materials used, well, these are the materials we have studied. So stainless steel, carbon fiber, nickel, polypyrrole, copper, and silver, and constantan. And in the right graph, you can see the various effects that have been achieved. Most of them are pretty much in line with what has been, what could be expected based on the Seebeck coefficients of the material. And you can see for the textile materials, relatively good outcomes, power outcomes can be achieved, although the constantan is the better one, but it's also not an easy material to work with, and it's not fully compatible with the textile processes. The textile structure, we have used carbon multifilament as a conductive core and nickel as the second material. The Seebeck coefficients of the materials are 3, and they should be -15. So we can expect a theoretical output voltage of around 18. And the carbon fiber has a moderate conductivity, which is needed to make sure the current is passing through the nickel coating in the dedicated area. And this allows to create such a thermoelectric effect by using a textile yarn inserted by a regular weaving process. The coating can be achieved either by local etching of a nickel coating on a nickel carbon fiber material, which can be just bought commercially via the internet, or by local electroplating of the nickel onto the carbon fiber multifilament. How did the models help us here? Well, first, on a material level, just give us an idea on the maximum achievable output, the material impact, both considering the conductivity of the materials as well as their Seebeck coefficients, the dimensions of the whole system, and then for the modeling, we needed to do some simplification, but we also managed to show that the simplification of the multi-filament into a monofilament with the same cross-sectional area of the carbon fiber and the nickel coating is allowed. It doesn't have an impact as long as a good contact can be guaranteed. And then also effects of the transition zone. You always have a transition between the carbon and nickel coated carbon. In an ideal case, this is 100% sharp, and there is no nickel in the intermediate layers. But with the modeling, we can estimate what would be the effect if this is not the case. Also, the effect of imperfections and local defects and inhomogeneous areas are to be included. Selective etching, here you can see some results. We had to elaborate a method for the etching because there was no literature. And here you can see how by increasing the concentration of peroxide, how the nickel is disappearing and how the carbon layer, the carbon core becomes visible. And in the right figure, you can see the resulting thermoelectric voltage as a function of the peroxide concentration. And you can see that as from a concentration of 10% peroxide, the nickel layer is fully removed, or at least it is removed up to an extent whereby you have an optimal functioning of the system. Then integration in a textile. Here the yarn has been inserted by hand because the etching has been done at the level of the fabric, and we achieved a thermal voltage of 16.7 microvolt compared to a theoretical maximum of 18, which is an efficiency of more than 90%, which is quite good. And the total voltage can be increased by having multiple pairs in series, which is a linear effect actually. The nickel coating has to be optimized because, of course, if the coating is not properly done, the outcome will be lower, and in some cases it can be as low as 3 microvolts. So it's really important to work on this in order to have a good result. In the right picture, you can also see how the voltage is increasing as a function of the temperature difference. It's a linear relationship, as could be expected. And here you also see that the model corresponds quite well with the experiment, and that the concentration of peroxide of the etching solution should be at least 10%. Then the testing. Well, the testing includes the functional properties and the textile use. And here also we had to develop methods for measuring the voltage and for creating the hot and the cold side of the fabric. So we used the hot plate and we allowed it to cool in air. So the ambient air was the cold side. And then to conclude, first general conclusion is that the energy scavenging as well as storage can be done by textile structures using textile materials and textile processes, and various principles are feasible. We heard in other papers that other concepts are feasible as well. We need an energy management strategy because energy is scarce and it's not easy to supply sufficient energy for powering a complete system. Modeling is useful, very useful to support the design phase. Test methods lack or need adaptation, and actually in November there will be an online conference on the topic of testing smart textiles and standards. Energy solutions largely depend on the application. Just remember the baby suit, whereby for newborn the inductive solution could be proper, but for elder babies this is not feasible anymore. And reliability is an issue. The conditions of textile use are really harsh. We sit on them, we stretch them, we bend them, we throw them in a washing machine with water and chemicals. So this is always a point of attention. So with this, I conclude my presentation. And if there are any questions, you can always ask them or contact me later, send me an email or a message, and I will try to help you. Thank you.
Thank you very much, Professor. Professor Liva van Langenhoven is a professor of functional properties of materials at Ghent University in Belgium. I would like to invite questions for her presentation. Do we have any questions for Professor? Thank you very much, Prof. Apparently, we have no questions at the moment, but like you have said, we can all channel our questions to your email address.
Yep, okay, no problem. And yeah, I would also like to congratulate the organizers for organizing this conference. I know it was supposed to be a physical conference, and I was really looking forward to visit your beautiful country once more. But in spite of the difficult situation, I think we still can enjoy an interesting program and learn a lot about novel developments in engineering. Thank you.
Thank you very much, Prof. We have challenges, but the challenges also give us new opportunities, so that we find that we are able to communicate and see results and share results of various activities. Thank you very much.
Thank you.
Okay. We have been listening to the keynote speech by Professor Liva. We will now go back to our program, and after the presentation of thermoelectric textiles, we go to the presentation on fabrication and acoustic performance of natural cellulosic fabric reinforced epoxy composites for musical instruments. This one will be is a paper by Fanshizi Liu. Fanshizi Liu, are you ready?
Yes, can you hear me?
Please go ahead and give us your presentation.
Okay, thank you.
If it's possible, you switch on your video so that we can also come close to your presentation if it's possible.
I'm Fan Shiziliu, a PhD student in the textile course. My superior is Professor Yiping Chou. My research direction is green textile composting. I'm honored to be able to share my work with you. The subject of
Just a minute, please.
Fabrication and acoustic performance. What?
Hello? Is it possible for you to switch on your video?
Yeah.
So that. Okay.
Can you see my video?
I don't see your video.
You can't see my video?
Please switch it on.
Fibers reinforced. It's okay?
Okay, just go ahead.
Epoxy composites for musical instruments. I will introduce my work from 4 aspects. Jump is the most important musical instrument of Chinese. There are more than 100 albums about drums. It presents an important cultural heritage of the Chinese nations. However, due to the large volumes of drums, it's impossible to board trains and airplanes. The transportation is very inconvenient. Moreover, a lot of wood is needed to make drums, but the forest is a very precious resource. To make 800,000 drums a year requires 400,000 cubic meters of wood, and 2.3 million 10-year-old trees will be cut down. If not, the carbon emissions of 618,000 cars can be reduced, which is very important for environmental protection. President Xi Jinping said local water and luscious mountains are invaluable assets. But there are thousands of rivers and mountains between them. How to replace wood with a musical instrument is our job. Using composite materials, such as man-made fiber and vegetable fibers reinforced composites to replace wood is in musical instrument has been attempted. It seems that composites are reasonably qualified for replacing wood in some of the musical instruments. In order to replace wood with fiber-reinforced composites in this instrument, acoustic emissions properties of composites have to be studied and compared with their old competitors. Drums need to meet some protections, such as metrical acoustics, dramatical stables, and processability. Especially the acoustic performance, we use 3 indicators to evaluate it, which I will talk about later. In our studies, 4 types of epoxy resin composites reinforced with the fabric of hem, flex, ring, and drift, respectively, are fabricated using Vancomycin resin infusion model, VARIM. The tensile protections of the composites was tested using a universal test machine instrument according to the ASTM D3039 standards. The flexural properties test was performed to the same machine according to the ASTM D7264. It can be seen that the strengths and models of 4 composite materials were larger in the weft direction than those in the warp directions, because the weft yarns were thicker and the weft fabric counts were larger than those of the warp. The The extrusion of the wood were particular variables, and the flexure strengths and the models of 4 composite materials were in between those of the vectors and the horizontal strips of the anthers. The crimps of warp and weft yarns in the composite materials could reduce the uniformization of the strengths and models of the yarn in the composite materials. It's obvious from that the web crimps of the 4 fabric composites were signified larger than those of the weft. Among them, hemp and flax weft yarns had little crimps, ensures a high rate of the fiber strength innovation, and the crimps angles of ram and jute were young weft yarns were about half of those in the warp yarns. This could effectively increase the tensile strength and models of the composites in the weft direction. The acoustic resistance and the reaction special characters of a material could be important indicator to evaluate whether it can be used as an antenatal materials for musical instrument. The special dynamic models ED rate rho, acoustic radiation dimensional coefficient R, acoustic impactance Z were calculated as shown. The acoustic properties of 4 composites were between those of horizontal strip and the vertical strip of the anthers. Since the flexure model of the composites was lower than and their density was higher than those of anthers, their acoustic dynamic models and acoustic radiation dynamic coefficients were lower, and the acoustic impactance were higher than those of the wood. The resonance frequency of the composites and the anthers all range from 0 to 5 kHz, and for all the natural frequencies of the composites were between those of the horizontal straight and the vertical straight.
Hello. Hello. We appear to have lost you, Francis Liu. Are you there?
Okay, I'm here.
Okay, continue.
Yeah, it's okay.
Continue.
Sorry, Chair, but we cannot hear the PPT.
Yeah, it's still.
I can't hear you. I don't know if others can hear you.
Guys, can you hear me?
Sorry, we cannot hear you.
Okay, I will share again.
Hear your voice, but no audios from your video.
Okay.
So Will you continue with the presentation?
Yeah. Okay. It's okay?
Continue.
We cannot hear the PPT. We cannot hear the sound. The Zoom sound.
Miss Liu, are you still presenting?
Yeah. You still can't hear me?
Now I can hear you.
Why? You still can't hear?
Fanchesi, please proceed on with your presentation. Hello? Hello? It looks like Liu Fanshizi has got a problem with her system. Is it possible for us to proceed ahead with the next presenter?
Hey, can you hear me?
Liu, is that you?
Yeah, it's me.
Yeah, I can hear you talking, but when you start presenting, I don't hear anything.
And 99%. Depends
okay,
for
continue. Okay, continue.
24 hours. Around 3.7 millimeters are used spectrographs. Our work is integrate the effect of recalibration impulse on test samples of composites. It can be seen from the spectrograph that whether it was hemmed or ram composite samples. Small boys with diameters of 3.5 millimeters, 4.7 millimeters, and 4.7 millimeters are used respectively. The resulting acoustic spectra after impacting were similar, and the characteristics at the wave frequency were very uniform. Only as the pressure increased, the amplitude shows an apparent trend. The two composites were pre-measured in advance. The humidity was set to 20%, 60%, and 99%, the time for 24 hours, and the performance of acoustic reaction test after the humidity adjustment were complete. The acoustic reaction spectra and the ram composites were different humidity prime conditions or combinations in the overall characteristics, and there was no missing or increasing appear. This proves that after pre-conditions of the humidity in 3 different humidification environments, the composites did not show a large change in interstrate structure. It can be found that the humidity of 99% and 20% of spectral circles having a rectangle higher degrees of constant weight. At the humidity of 16%, some peaks circles become high, some become low. It may be that the after-water molecules enter the composite materials. It caused a certain change in their density. At present, we have produced a first describable green composite room, and we will continue to import it later and cooperate with the company for mass production. Through research, we found that natural cellulose fibers may become sustainable for wood and it ideal sustainable for nation-present instruments. But if its acoustic performance is to be exactly the same as the wood, there's still a lot of work to be further studied. Thank you for listening to my report, and welcome to continue with me. Thanks.
Thank you very much, Liu, for your presentation. I appreciate that you had some technical challenges, but I think this did not interrupt or the understanding of your presentation. Thank you very much. Is there anybody with questions for Ms. Liu? If not, we shall proceed on to the next presentation. And the next presentation is on the design and development for polymeric optical fiber textiles via Jacquard technology by Dr. Lange. Dr. Lange, you're there?
Yeah, I'm here. Can you hear me?
Please present.
Okay. Can you see my PowerPoint?
Yeah. If it is possible, please switch on your video. Please switch on your camera.
Okay. So I think it's a bit dark.
Thank you. I can see you.
Okay. It's a little dark. All right. I'll start. You can see my PowerPoint right now.
Yes.
Okay, so hi everyone, my name is Golan. I'm currently a PhD candidate from the Hong Kong Polytechnic University. It is a great honor for me to attend this symposium. The topic that I would like to share with you today is design and development for polymeric optical fiber textiles via Jacquard weaving technology. So my presentation today will cover 4 major aspects, which are evolution of weaving, introduction of smart textiles and polymeric optical fiber textiles, research background, and major design challenges for weaving POF textiles. As we all know that weaving is an ancient craft and technology which has been around for thousands of years. This slide presents some representation of woven pieces from ancient China, Africa, and Egypt. So traditional hand weaving has always been a very slow process which requires a lot of time and labor. One single piece can take the artisans months or even years to complete. So during the Industrial Revolution, Jacquard weaving technology was invented by Joseph Marie Jacquard in the early 19th century. It transformed weaving manufacture from craft to industry production. So the weaving manufacture speed has been largely increased with the invention of Jacquard technology. Up to today, in this digital age that we're living in, weaving industry is embracing its new life. In 2016, Google partnered with Levi's to create a new interface, interactive interface, which allows the user to wirelessly control their smartphones just by touching their clothes. Textile materials, as the most intimate materials in people's daily lives, have achieved new performance and design values during the past decades through the integration of advanced technologies. Particularly, smart photonic textiles has been given the capability to display illuminative colors, patterns, and texts from light emissions and has been adopted in different applications, ranging from fashion design, home furnishing, healthcare, and safety uses. So my work will focus on one type of the smart textiles, which is POF textiles, shortened for polymeric optical fiber textiles. POF textiles are produced by directly integrating optical fibers into the textile fabrication process, thereby providing unlimited possibilities in terms of surface design and tactility. It shows its advantages of lightweight, low cost, flexibility, and low power supply in comparison with the other types of photonic textiles, such as LED embedded photonic textiles. The surface light emission is enabled by microbending of POFs or cladding damages to POFs. However, it is important to be aware that POFs can be susceptible to damages from severe bending, which is one of the major challenges. The fabrication methods include embroidery, knitting, and weaving has employed by practitioners and researchers to produce the POF textiles. However, the fabrication methods of knitting and embroidery require looping yarns, which can damage the POFs due to severe bending, which will lead to very short light travel distance. By contrast, woven textiles are formed by interlacing yarns with one another. This process involves less bending, hence it causes less damages to POFs. Therefore, weaving technology is more suitable for producing larger scale POF textiles. And some POF textiles and prototypes have been designed, developed, including some prototypes by Dr. Jeannie Tan and then Ziqian Bai. However, the prototypes is quite bulky and needs more variation in terms of appearance and tactility. And furthermore, the preparation process is still very time consuming, which prevents it from adapting for the mass production. And then some other photonic textiles integrated with optical fibers have also been developed by other designers and studios, including Malimba Baktada, XX Labs, Dreamlux, and Zach Poser. So based on the review of existing works in the field of PUF textiles, we can see that the new functions are enabled for PUF textiles with the integration of electronic textiles. However, the integrated electronic components add to the bulkiness of the design, which affects the usability and appearance. And then the electronic connection process is still laborious and time-consuming. And weaving plays a very important role in the development, however, has been neglected from the existing research. So, and then the current PUF textiles are still, the properties are still rather limited, and most of them are still in planar and then the single layer form. So more complex woven structures with multi-layer should be developed for new design solutions for the electronic integration as well as the enhancement for the new properties. So as we know that, so for the PUF textiles, there are new design elements such as conductive yarns, power supply, microcontrol system, LED, and optical fibers that are integrated, which is very different from the traditional jacquard weaving fabrication process. So there are new design challenges and that we incur for the development of PUF textiles. So from the weaver's perspective, there are three main aspects, including the for the new challenges, including the optimizing new performance, integrating with electronics, and seamlessly and placing the functional yarns to meet both aesthetic and technical requirements. So here I'm going to present four major challenges for my research, which covers the seamless electronic integration and new properties for PUF textiles, and then the weave design for multi-sensory environment. So the first design challenges to overcome is to develop a new weave design method to achieve more seamless electronic integration. So in order to connect with the electronics, PUF fringes need to be created and separated from the rest of the yarn system. So the previous method of creating the PUF fringes require manual labor, and it's very it is very laborious and time-consuming. So I created this new this three-dimensional compound weave using the floating technique, which enables the automatic separation of the PUF floats and then the other textile-based yarns directly via the jacquard weaving fabrication process. So this new weave technique have eased the electronic connection, and it enables development of PUF textiles in one process, and which has significantly reduced the time and labor. However, this new weave solution have cause more issues during the weave production process, because it causes the great difference in the warp tension between the center motif and then the PUF fringe areas, which has slowed down the weaving production process with the a lot more like dropped wires. So in order to solve this production issue, a more balanced weave combination has been designed for smooth weaving production, which is illustrated on the left of the slide. In addition, a lock section woven with plain weave is designed in between the center motif and the PUF fringes to avoid the PUF fiber slippage. And then the next experiment have successfully fabricated the PUF textiles with new property of three-dimensional effect and stretchability. And so the three-dimensional effect of PUF textiles have increased the diversity in aesthetic and tactility, and it also offers more versatile visual and tactile experience for the users during the interaction. And then the new property of stretchability has contributed to increase the comfort and flexibility for PUF textiles. And then So these new properties are enabled by using the double weave combined with spandex and suitable motifs. So the motif was designed in wavy pattern to allow for the space for spandex to shrink. And then the stitched double weave and then is alternated with unstitched double weave. And as we can see on the left right corner, and then the white space, the white section is designed with unstitched double weave, and then the black section is designed with a stitched double weave. So the spandex at the unstitched double weave section can shrink at the bottom with the POF puckering out on the top, which create this three-dimensional effect. And and then the weave design is also shown in the diagram on the right side with the cross-sectional view as well. And then this is this is how this new POF design, how this design is applied onto fashion pieces. And then the next design challenge is to enhance the touch-sensitive function of POF textiles. And then two interactive cushions are developed, which are named Sensi and Cappy. And several major weave design aspects are tackled, including the design for capacitive sensing areas, and then the design for the surface textures and interactive sections, and as well as the electronic connection, and then more balanced weave combination for smooth production. So the touch sensing ability is enabled by directly weaving conductive yarns at the designated areas, which replace the foil paper in the previous prototypes. For cushion cappy, 3 interactive sections in diamond shapes are designed as the touch-sensitive buttons, and then the illumination of the cushion will be activated by touching the diamond areas. Similar design principles and weave approaches have been applied to cushion sensi, and a different appearance and texture has been achieved. And this is to show you how the interactive function works with the designated areas, and then the illuminated views of these 2 interactive cushions. And then the final design challenge is during my study is to develop POF textiles for the multi-sensory environment. So this project is collaborated with a Dimension Care Center in Hong Kong. A diversity of tactility and appearance was created for this interactive panel to provide sense stimulations to benefit the elderly through visuals and touches. So double weave and novelty yarns are combined to create distinct textures for the POF textile pieces. And the motif designs were co-created with the social workers and elderly in the care center, which reflects nature and local cultures. The versatile of the POF textiles became effective stimulations to trigger positive emotions for the elderly. So to sum up my work, so interactive polymeric optical fiber textiles serve as flexible illuminative materials, and it provides a dynamic visual appearance with its unique illuminated quality. So with the advantages of lightweight and flexibility, so optical fiber is a very suitable material and can be fabricated through traditional jacket weaving to achieve the interactive and illuminated functions. And then the new weave design approaches can bring enhanced properties and performance for the POF textile, as well as more seamless electronic integration methods. Okay, so that's the end of my presentation, and thank you very much for your attention. If you have any questions, I'd love to answer them. Yeah, thank you.
Thank you very much for your presentation. I am sure everybody enjoyed the discussion, particularly on the designs that are possible on the jacquard with the optical fibers. Do we have any questions for Dr. G? Okay, do we have any comment, any suggestions on the presentations that have been presented today? Thank you very much, Dr. Lanji. We will definitely get back to you in case we want further information on your projects. Thank you very much.
Thank you.
The time now, it brings us to the end of the session, and we are supposed to take a break. And this break, I think if you have your program, it will be possible for you to see the link to the break. Okay, thank you very much.
Good afternoon, members. Good afternoon.
Good afternoon. Good afternoon, Prof.
Thank you.
Good afternoon, sir.
My name is Simiyu Sitati. I'm the chair of the next session. After this session that has just ended, the next session is supposed to proceed on this same platform where we are having 4 presentations. And the presentations are from the following persons. I'm just going to give you them. Dr. Jerry Ochola, are you in the house? Dr. Jerry Ochola?
Yes, Prof. I just raised my hand.
Oh, good. Then it will be followed by Musinguzi Alex. Then we shall have John Darkwa and Juma Simiyu. This session was supposed to continue immediately after the one that has just ended. As members proceed for break, others, you are also welcome to continue with us here. And I don't know whether my co-chair is in, Brenda. Okay, my co-chair will join us later. So we request the previous presenter to remove the presentation so as Dr. Jerry can be able to put his presentation. Dr. Jerry Ochola. Dr. Chola is going to give us a presentation titled Numerical Modeling and Simulation of Thermal Bond Reinforcement Using Braided Structures.
Bond reinforcement using braided.
Sorry, Prof. I think I lost your sound or my sound.
Dr. Chola, Please go ahead.
Thank you, Chair. My name is Jerry Ochola. I am a lecturer at Moy University, the School of Engineering. Professor Michele Conti and I have been working on a project on the numerical modeling of fractured bones, specifically the femur. The project actually was funded in collaboration with the University of Pavia. The femur is just the bone that joins the pelvis and the knee. And like many other bones in the human body, it's actually used for support, but mostly it's actually important in movement. And not only found in humans, it's also found in other animals as well. So you can actually call the femur bone the thigh bone. Yeah. So the fact that this bone is actually used for day-to-day movements, it's actually prone to a lot of fractures. Most of the times the femur bone is under tension, and when it's under tension, it will not often crack, mostly due to actually overloading. And sometimes it also not only cracks due to tension, but also compressive forces. When the bone undergoes compression due to weights or loading, it will tend to shear at its shaft. And at times also you also discover that when or due to accidents, the bone can also undergo twists or what you call torsion, and therefore it can also crack in the direction of twist. So the biomechanics of femur fractures is actually mostly affected by tensile forces, compressive forces, and also torsion. And all these forces or loadings occur when the bone is under or during the use of the bone, which mainly is under support or actually movement. So this actually necessitated the need to actually repair the bone. Now currently the bone is actually being repaired by the use of intramedullary nails when it's actually cracked at the shaft, or plates when it's cracked in the head regions, and also screws. But as you can see on the picture on the right here, for you to actually do the fixation, you actually have the fixator to actually bring the broken ends of the bone together. So this has made the process of bone surgery quite involving and sometimes time consuming, because you have actually first to look for the fracture of the bone, and then bring the two ends together, and then put in the intramedullary nails. What you can see at the bottom right picture, the far right picture, is where now the two ends have been fixed together by an intermedullary nail. So it makes actually the whole process of bone repair a bit costly, mostly for patients that are in most parts of the developing world. Now, this actually has made there being a need to actually look for an alternative to actually this long process of actually bone repair that could actually make the process less complex, cheap, and actually efficient. Most studies have actually tried to look for an alternative. Most authors have actually tried to look for an alternative to this process that actually is illustrated here, which I've actually just summarized. It's actually more complicated than actually this. One of those approaches has been the use of structures called braided structures. Braided structures are actually tubular structures that are formed using fibrous manufacturing processes, and they've actually been used, or there have been trials of using these processes in orthopedic tissue repairs. There's actually evidence in these trials that the braided structure can actually hold orthopedic structures such as the bone together during repair. What happens is that when you hold the two broken ends together, due to bone remodeling, the fractured site will actually heal, and then the nails will be removed. The braided structure can actually come very, very close. Now, in this case, therefore, we also came up with an idea of actually trying to use the braided structure or demonstrate the feasibility of using the braided structure in actually femur bone repair. In our study here, we are actually looking at the load, deflection, and stress distribution, and we are just using numerical or mathematical algorithms to look at the feasibility of this method. And we actually investigated the single stance configuration. So the braided structure, as I've said, is a tubular structure. We created the model or the 3D model of the braided structure by actually trying to look at or compute the yarn part or the path of the yarns in a 3D interface. And then after that, we used a finite element analysis platform, the Abacus version 17, to try and simulate the deformations in this structure. So we actually computed the X coordinate, the Y coordinate, and the Z coordinate of the yarn. And then we computed all the yarns in the braided structure. That is the algorithm or the formula, the second formula in this particular slide. So the illustration here is just a single yarn, and then we actually did a transformation, a mathematical transformation of all the yarns in the structure and the cylindrical shape. So eventually we had a model like the one on the top left, whereby we had the braid angle, and the braid angle is actually the angle between the yarns in the anti-clockwise and the yarns in the clockwise. And then we have the braid diameter and also the length of the braid. Figure B here is actually the braided structure that we computed using the Python language. What I didn't mention is that the program we are using here is the Python programming language. So that's actually what we used to actually compute or generate the structure here in the bottom left. We also generated the 3D model of the femur bone using CT scans of the human femur. The picture on the right. And then we remove the distal femur or the base, the bottom side of the femur that joins the knee. And we only focused, or we only used the femur shaft and the proximal head, because the fracture that we wanted to simulate was on the femur shaft. So we actually removed the distal femur and only did analysis on the shaft and the proximal femur. So after we generated the CT scan, we removed the spongy components of the femur and only simulated again the cortical bone. So in this particular study, we are only looking at the hollow bone. Remember, the human femur has the cortical exterior, which is actually shaded dark in this particular illustration. And then there is the bone marrow and the spongy components, which is actually inside the cortical bone. So in this particular study, we only considered the cortical bone or the outer surface of the bone, and then we used the hollow bone. We actually used an 4-node tetrahedron element for our finite element analysis. What you see here is just the dimensions of regular human femur. So the reinforcement in our study was actually done by actually trying to reinforce the bone. Instead of now using the nails and the plates, we actually try to cover the fractured site of the femur bone using the fabric or the braided structure, the tubular braided structure. One, to actually try to ensure that the structure is strong enough to support the two ends of the fractured femur. More or less what the surgeons or what traumatic orthopedic surgeons are doing today, but now we actually trying to eliminate the nails and ensuring that the braided configuration or the braided structure can actually support the bone during repair. The boundary conditions that we applied during our analysis, okay, was first we were trying to do quasi-static structural loading of the bone. Quasi-static structural loading is the case whereby you actually balance the forces, the internal forces, the kinetic forces, to actually to ensure that the simulations are actually not affected by external forces, and that the loading is actually smooth, so to speak. So in this particular case here, we introduced a fracture at the middle of the bone or on the bone shaft, what you see here in figures of C. And then we, in the loading configuration 1, we apply load at 90 degrees. What you'll consider here as the fall configuration. In load 2, we applied the forces at 120 degrees. What you'll consider here is as a single stance configuration. The amount of force or that we applied here was 800 newtons, which is approximately the weight of an adult human. Now, something also that we did in our boundary condition applications is that we balance the joint reaction forces that come from the hip with the abductor forces on the bone. Our findings are that when we loaded the bone, or when we applied a load that displaced the bone by 35 millimeters, there was a lot of deflection in the bone in this single stance configuration, as opposed to when the force was applied at 90 degrees. This one happened in the intact bone, and also it also happened in the fractured bone. The fractured bone results the contour plots on the top right. On the top left, you get actually the intact. Oh, sure, we actually illustrated. We also saw these results when we did our loadings in the reinforced bone. On the bottom left here, the reinforced femur is actually the femur plus the braided structure. We actually eliminated the braided structure to look at the contour plots on the bone due to actually the reinforced structure or the reinforced fabric. Now, one thing you'll actually see here is that the deflection after reinforcement here reduced significantly as compared to the intact bone here. It means that the braided structure offered some support to the reinforced bone. Remember, the reinforced bone here is actually the fractured bone plus the braided structure. So what you see here in the bottom right picture is actually the structure that has a fracture and the braided structure. And you will discover that is actually the deflection is actually reduced, or the deformation in the bone is actually reduced compared to the intact bone. The mechanical analysis actually illustrated that comparing the intact bone or the bone before the fracture with the bone with the fracture, the rate of increase in the load displacement was actually more in the single stance, or in the theta is equals to 120 degree loading configuration compared to the theta is equals to 90 degree loading configuration. We also learned from our results, or our results also show that the fractured bone had almost no no resistance to actually loading, well, because of the fracture. But sorry, when you look at the reinforced bond or the bond with the braided structure here, even though the rate of increase of the loading rate was actually almost identical to the bond before the fracture, the reinforced bond, the bond that had the braided structure, withstood more stresses than the bond with before the loading. Now this again suggests that the braided structure had some contribution to the mechanical properties of actually the bond. It actually offered some resistance to loading or some stiffness to the bond, so to speak. So these two illustrations, when you look at the bond with the structure, with the fracture, those are the graphs at the bottom of this particular slide. And then you look at the bond now that has with the fracture but reinforced, you actually discover that the bond stiffness actually improved. In this regard, therefore, we actually believe that the reinforcement of the bond using the braided structure could offer some support to the fractures in the bond, or some stability, so to speak. We actually learned that the strength of the bond increased, and also its stiffness. This only suggests that a study in this particular direction can actually offer some solution to bond repair that, or the bond surgery that is actually being done today. Finite element analysis or numerical analysis, that approach that we used here, is also a feasible way of actually doing these particular studies. They can actually give light to the bond repair studies in vitro. Those are some of the citations that we had. Thank you very much, Chair.
Thank you very much, Dr. Jerry Ochola, for that insightful presentation. At this moment, we invite some 2-3 questions from the listeners, please. Anybody who carry your hand if possible? Any question? Looks like the presentation was very, very clear to all the people, and therefore no questions are forthcoming. Jerry, yes, I might ask you a provocative question. Can I gain weight to the extent that it can exceed the strength to carry the bone can break?
Well, thank you. You can actually not gain weight more than your bones. The body has a way of actually balancing its own systems. The more you gain the weight, the stronger your bones actually become, by the way. The body actually communicates with all the systems in place. So as you gain weight, your bones also get stronger and stronger and stronger. As you lose weight, again, they become weaker and weaker. That's why when you get old, for example, your bones, they weaken or their quality goes down. So that is actually how the body also try to balance its system. So there's no way that your bones can one day crumble.
Oh, thank you. Thank you for the reassurance.
You're welcome, Prof.
Thank you. So now we get to the next presenter, who is Musinguzi Alex. Musinguzi Alex is coming to give us a presentation on antibacterial. Just a minute. Giving us a presentation on antibacterial efficacy of the aqueous and ethanolic herbal extracts from Datura Stramonium, Racinus communis, and Galisonga parviflora plant leaves. I don't know whether I've pronounced well. Musinguzi himself will come and pronounce for us the right way.
It's very
Musinguzi,
fine.
yes,
Yes,
please welcome.
Thank you.
You can show us your face so as people know who is presenting.
Okay.
Good. You're welcome.
Thank you. Good afternoon to all. Musinguzi Alex is my name, presenting to you my research findings under the topic antibacterial efficacy of aqueous and ethanolic herbal extracts from the Trastronomium Racinus communis and Galisonga pavifera plant leaves. Healthcare-associated infections are as a result of germs entering your body during medical care. These infections are considered to be the second leading cause of death worldwide, whereby 4 million people have died in Europe and 7 million people in USA.
Alex.
Yes, please.
Alex,
we can't
Yes,
see the
please.
We can't see your presentation.
I shared. Let me share again.
You can remove your video and share it now. Good.
Has it come?
Not yet. Yeah. It came and disappeared. Yes. Now it's there.
Has it come? It's there. Okay. What about now?
Yes, we can see it.
Okay, thank you so much. I'm sorry for that. Once again, I'm Alex Musinguzi, presenting to you antibacterial efficacy of aqueous and ethanolic herbal extracts from the Trastronomium Racinus communis and Galisonga pavifera plant leaves. As we are all aware, healthcare-associated infections are normally as a result of them or germs entering your body during medical care. These infections are also considered as the second leading cause of death worldwide, whereby 4 million people have died in Europe and 7 million people in USA. These infections have proven to be resistant to most antibiotics used. In a bid to overcome such challenges, Plant Kingdom have been opted for due to its antibiotic resistance inhibitors facilitated by their variety of phytochemicals and other compounds contained within them, their pharmacological properties, they are economically viable and are eco-friendly in nature. Having my main objective as to evaluate the effect of the Trastronomium Racinus communis and Galisonga pavifera plant leaf extracts on Staphylococcus and Pseudomonas bacterial strains, then my specific objectives are to prepare plant extracts using aqueous and ethanolic extract methods, and also to evaluate the antibacterial efficacy using disk diffusion and serial dilution methods. This study will indeed help to discover bioactive dyes which are eco-friendly, non-toxic, and non-allergic as a replacement synthetic dyes. It will also address healthcare-associated infections, as well as add on a number of possible medicinal plants discovered so far. In my methodology, we collected plants from western part of Uganda, whereby their leaves were dried under the shade and grounded into coarse powder, as can be seen in step A. Then step B, we mixed the coarse powder of these leaves with water and ethanol and left them to settle for 15 minutes. Thereafter, they were introduced into a water bath, which was set at 50 degrees Celsius, and they were left for 24 hours for extraction to take place. Then on step D, the extracts were filtered and concentrated in a rotor vapor in step E to remove the water and ethanol that were used during extraction process. Then another step, inoculum was prepared in a Muller-Winton agar at 37 degrees Celsius for an overnight, followed by antibacterial activity tests that were done using disk diffusion method as per Cabaibo test protocol. Then minimum inhibition concentration tests were done using serial dilutions as described by Finch and Tell with slide modifications. In the results, the mean values of zone of inhibition obtained from aqueous and ethanolic extracts against Staphylococcus and Pseudomonas bacterial strains were structured in a table format, whereby we have the aqueous extract tending to have bigger values compared to ethanolic extracts. And this was further clearly illustrated in a graph. As we can see in our graph, aqueous and ethanol extracts exhibited varied antibacterial activity. Then there, with better zones of inhibition registered with aqueous extracts, which ranged from 8 to 18 millimeters, as compared to ethanol extracts, which ranged from 6 to 13 millimeters. Also, it was confirmed that high activity was against gram-positive bacteria as compared to gram-negative bacteria. Antibacterial activity of the control confirmed that indeed distilled water and ethanol didn't have any influence on the inhibition zones obtained as compared to standard antibiotics like amikacin and ciprofloxacin, whereby for them they had activity against the bacterial strains. Still on results, aqueous exhibited the lowest minimum inhibition concentration, which was at 3 milligrams per milliliter as compared to ethanolic extracts, which showed 30 milligrams per milliliter. The negative sign indicated that there was no bacterial activity, and the positive sign indicated that there were bacterial activity present. In our discussions, it was confirmed that the presence of varying phytochemicals contained within the extract led to the variations in bacterial growth inhibition. Also, it was confirmed that bigger zone of inhibition for aqueous extracts compared to ethanolic extracts was indeed as a result of the variations in the ability of the solvent to dissolve the grounded plant leaves. Then the differences in morphological nature of microorganisms, it was further found that it influenced the activity recorded against the gram-positive and gram-negative bacterial strains. Then the presence of varying phytochemicals like cyanogenic glycosides, among others, might have contributed to the lowest minimum inhibition activity for aqueous as compared to those ones obtained with ethanolic extracts. Then the research will help in preventing the growth and transmission of microorganisms in the healthcare environment, as well as steering the increase in production of these medicinal plants for dye production. Also, this research will create jobs for the locals, thus improving their standards of living. This research was concluded by confirming that aqueous extracts of selected medicinal plant leaves demonstrated bacteriostatic activity against the selected bacterial strains, thus justifying the persistent use of these herbs in traditional medicine. Thank you for listening.
Thank you very much, Alex, for the presentation. Very good presentation. Now I know that when I get the herbs, they can kill bacteria.
Yes.
Now we open the floor for listeners to comment, ask question? Any question from the listeners? Hello, are we there? Good, Alex?
Yes,
Jerry?
please.
Daktari, please.
Yes, Prof. Let me ask a question. I think, Alex.
Yes, Doctor.
This is a good job that you're doing in Uganda. But in Kenya, do we also find, my first question is, in Kenya, do we also find this strain of herbs that can actually give you these antibacterial properties? And two, again, to your table, the table with a lot of pluses and minuses. Sorry, I couldn't get the slide number. That table. In this table here, nothing seems to be happening between 0.3 and 0.003. Okay, if it's all negative, it means that there's no activity here, so to speak. So why did you consider this level? Why couldn't you just consider between 30 and 3, where there's a lot of activity? In my opinion, why did you consider this other zone of the yes? Alex.
Okay, thank you, Doctor. I considered those 5-fold aspects for concentration to show that there is no chance of obtaining any activity beyond 3 milligrams per milliliter concentration, so that someone can really see that when you go beyond, indeed, there is nothing. They are living there, and someone can suspect that, what if you continue? Wouldn't be there something? So that's why I did a number of them ahead to prove that indeed there is nothing that can happen.
Good.
Sorry, Alex. Let me just sorry, Prof. Let me just help
you.
Go
ahead, Alex. Go ahead, Jerry.
Let me just try to help you. From 0.3 beyond, like 0.3
yes.
to 0.003 to 0.001 is actually 0, So if you just stopped at 0.3, nobody will actually doubt your data. Sorry, your experimental designs. They don't add value, in my opinion, because it's like writing 0, then 0, then 0, then 0, then 0, because you want actually to actually like insist or exaggerate your results. If you actually did your study between 30 and 3, it will give somebody a better idea of the activity or the concentration of in this area than presenting 0 so many times. So maybe to help you, just go ahead and do an experimental analysis or experimental design between 30 and 0.3, for example. It will make your results more interesting than presenting the so many zeros beyond. And do they find these ones in Kenya? Do you find these plants in Kenya?
Yeah, in Kenya, no, they are not there.
Okay.
I tried searching around, I could not get. Since they were available in Uganda in large quantities, I opted to pick them from around Uganda.
Okay.
Then for your idea, I've taken note of it. I will for sure work on it. Thank you so much, Doctor.
Okay, you're welcome. Thank you, Chair. That's all for me.
Thank you very much, Alex, for that presentation. I can see there's more question from Mike Tebietekerwa. Please, Mike.
Yeah, thank you very much. And thank you, Jerry, for asking the previous question. I'm going to add on that. And Alex, I'm wondering why you started from 30 also. Why didn't you start from 60?
Okay, thank you, Mike. I started on 30 because my concentration I obtained after evaporating the liquid was starting from 30 milligrams per milliliter.
Come again?
My concentration after removing the ethanol and water was starting from 30 milligrams per milliliter. So I moved like that. So I never started from 60 because I was not reaching there.
Okay. Professor, you are muted. We can't get you.
Okay, sorry. Thank you, Alex, for that good presentation.
You're most welcome.
We thank you for availing time to present to us.
Yes.
Now we go to the next presenter. Thank you so much.
You're most welcome.
Our next presenter today is John Darkwa, who is coming to give us a presentation on Bayesian for simple and generalized linear models, comparing INLA and MCMC techniques. Please, John Darkwa, are you around?
Yes, please.
Thank you. Now you, Alex can remove the presentation to allow John to put his presentation. So, John, you have 15 minutes for presentation and 5 minutes for us to clarify, ask questions, and so forth. Please welcome. You may put your camera temporarily so as people can see who is presenting, and then you remove it.
Okay. So yes.
Yes,
Can
John.
I be seen now?
Yes, we can see somebody somewhere. Please go ahead.
Thank you. And
yes.
are my slides also visible?
Yes, we can see your slides.
Okay. Okay, great. So I am John Darkwa, and I'm presenting a paper on Bayesian inference for simple and generalized linear models, comparing.
Excuse me, John, presentation mode, please.
Sorry?
Can you put in presentation mode?
Oh,
yeah.
No problem. Are we good?
Much better, thanks.
Great. So I'm John from Moore University, PhD student in biostatistics, and I'm presenting a paper on Bayesian inference for simple and generalized linear models, comparing NLA and MCMC techniques. NLA is actually an acronym for Integrated Nested Laplace Approximations, and MCMC is an acronym for Markov Chains Monte Carlo. So these are things I would like to compare. Now, in inferential statistics, all we try to do is to do point estimations, interval estimations, and hypothesis testing. Point estimations like finding the mean, and interval estimations has to do with confidence intervals and so on and so forth. Now, there are two main schools of thought when it comes to these inferential statistics. We have the frequentist school of thought, and we have the Bayesian school of thought. These two schools of thought vary in their conceptualization of probability. Whilst the frequentist school of thought sees probability as a limiting frequency of an experiment repeated infinitely, the Bayesian sees probability as a subjective quantity which depends on the availability of information. Now, in inferential statistics, if one follows procedures very well. It's amazing that these two schools of thought end up giving the same estimations. Now, to carry out this inferential statistics, we normally use mathematical models, and these models are generally classified into two main groups. They are either simple linear models or generalized linear models. The difference between these two models is that whilst a simple linear model, the response variable or the data is seen to be normal. The generalized linear model has the data being a non-normal conditional distribution. So these are the differences in there. So basically, if we talk about a simple linear model, then we're talking about a model that has the response variables being normally distributed. And then these are the ones which fall under generalized linear models. They have their response variables not normally distributed. So they can be Poisson, they can be binomial, and so on and so forth. Now, when we zoom in into Bayesian inference, there are three main distributions that are very, very critical. One is the prior distribution, which has to do with the prior knowledge we had about the parameter we want to estimate. And then the likelihood is the data we collected, the information we have about the present information we have about the parameter. And when we multiply these two, we get the posterior distribution, which is the probability of the parameter given the data. So the likelihood is the probability of the data given the parameter. So any inference that is carried on the parameter you want to estimate is carried on the posterior and not on the likelihood nor the prior. So to be able to estimate any parameter using the Bayesian approach, there are several ways of getting it done. But the mother of them all is this Mcmc, that is Markov chain Monte Carlo technique, which basically depends on Monte Carlo integration, and it has several other softwares that have been developed to use the Monte Carlo integration idea, and some of them are OpenBax, which was developed in 2009, JAX, which was developed in 2003, and Carbase, which was developed in 2013. But lately, there has been another approach for carrying out Bayesian inference, and that is integrated nested Laplace approximation, and that is INLA, and it uses numerical integration. Now, the reason for this comparison will be made clear in our objectives. We're going to use the R software for this simulation study. Now, the aims and objectives as follows. We want to compare MCMC and INLA performance in simple and generalized linear models. And then the objectives are that we're going to compare their performance in terms of the accuracy of the parameters they estimate, the time, the computational time of estimation, and then the computational burden, how much work has to go into the process. So the main justification for this study is that we want to put it forward that INLA is a good substitute for Mcmc in vision inference. This because Mcmc has a lot of cumbersome approaches that one will have to embark on in order to be able to finally estimate the parameters of interest. But INLA is a bit easy and it's not very time consuming. And we'll see that in this presentation. So the methodology, when we look at the simple linear model, we have a model that is as simple as it is. It just as the name sounds, linear. So it's just the equation of a line, basically. And then this in matrix notation. So y, which is a response vector, and x is the covariate or design matrix, and then the beta we see there is a vector of the parameters we want to estimate, and the noise there is epsilon, and it's considered to be normally distributed with mean 0 and equivariance variance matrix, which is a diagonal matrix of the variances. Now, the setup for the linear model is that we had to define the posterior distribution, and after defining the posterior distribution, which was the product of the likelihood and the prior, we had to also determine the full conditional distributions. In this case, the likelihood was given a normal distribution. The prior distribution for the Bdms was given a flat distribution, and the sigma squared, which is the next parameter we need to estimate, was given a gamma distribution. Now the full conditionals were determined to help us estimate these parameters. And when we determined the full conditionals, we realized that they were in closed forms. Closed form means that the distributions we got were standard and known distributions. And for that matter, we use the Bayesian the MCMC algorithm called Gibbs sampling for the running of the MCMC technique. Now, for the simulation, we had the model set as y being equal to 1 plus 2x plus the noise, which normally we term as the random effect of the model, and 1, which is the intercept, and 2, which is the slope, tend to be the fixed parameters. And if you look at the random effect, sigma in this case was set to be 1. And in order to make the Bayesian process very objective, we use non-informative priors so that the posterior distribution will be dominated by the likelihood, which is the data we have collected. When we consider the generalized linear model, we also had a model set up as you see on the slide, that in this case the response variable was not normally distributed, but it has a Poisson distribution, and we coined this from a disease mapping where we're looking at a certain number of regions that has a certain number of diseases. So we have the observed count and then the expected count. The expected count per region is the capital EI, and then the observed count is the one defined here as the coordinate, the transpose of the covariance times beta. Now the setup for the MCMC was just as we did for the simple linear model, but in this case, after finding the posterior distribution, we had to embark on a second order Taylor's series to find a proposal distribution, just because the posterior distribution for the generalized linear model was not in closed forms, so it was difficult to sample from them. So when we did the approximation, we got a proposal distribution from which we were able to also deduce the full conditionals, and they turned out to be in closed forms. So when we consider the generalized linear models and then the simple linear models, in both cases we want to estimate the betas, which are the slope and then the intercept. We did not consider the random effect in the generalized linear model in this study, but we considered it in the simple linear model. Now, for the simulation study for the GLM, we actually set the model as the transformation of the mean, which is the log of the log being equal to 1 plus 2 CI. The CI, we're talking about the covariates, and we mean centered them so as to help the goodness of fit of the model. So in this other case too, we've set the intercept as 1 and then the slope as 2. We again use non-informative prior with the idea that we don't want the posterior distribution to be partly influenced by the prior distributions we chose, which are in themselves subjective. So we wanted the likelihood, which is the data we generated, to dominate the posterior distribution. For INLA, it was a straightforward approach. All we needed to do was to get or establish a relationship between the response variable y and the covariates, and then identify the data that these two variables can be found in, and then apply the INLA function. And this was same for the simple linear model also. Now, the results are as follows. For the simple linear model, we are looking at the convergence diagnostics and estimates. And in this case, for MCMC, we need to make sure that the chain converges. And to help us ascertain whether the chain converged or not, we have to have a trace plot and an an autocorrelation plot. And there are graphs as we see on the screen. Now, the parameters we estimated as follows. We see that the true value for the intercept was 1, the slope was 2, and the variance was 1.0. Now, INLA estimated the intercept as 1.281, whilst MCMC estimated the intercept as 1.283, and both of them had a standard deviation of 0.11. If we consider the slope, which is beta 1, we see that MCMC estimated the slope as 2.097 with a standard deviation of 0.12, and INLA estimated the slope as 2.098 with a standard deviation of 0.12. And when we look at the tau, which is actually the precision, that we see that the precision is also defined as 1 over the variance. So we had to set it this way because that's how INLA has been formulated. So we needed to formulate MCMC in the same way in order to help us compare them. Now, the true value, as I've already said, was given to be 1.0, was set as 1.0, and INLA estimated it as 0.907 with a standard deviation of 0.13, and the MCMC also estimated as 0.907 with a standard deviation of 0.13. Now, for the generalized linear model, we also had to do same for the convergence of the MCMC, and the convergence, the trace plot, and then the auto correlation plots as we see, and then the parameters we estimated for the intercept, the true value was 1, was set as 1, and MCMC estimated as 0.979 with a standard deviation of 0.06, and INLA estimated it as 0.979 with the standard deviation as MCMC. When it comes to the intercept, the slope, we see that the true value was set as 2, and MCMC estimated as 2.016, and with a standard deviation of 0.04, and INLA estimated it as 2.016 with a standard deviation of 0.06. For the let me do the discussion right here as I move on, because of the nature of the animations of the slides. Now, when we look at the convergence diagnostics, we see that for the autocorrelation plot, the chain moved away from its initial value rapidly, with the sample path wiggling vigorously in the area supported by the distribution of the parameter, an indication that the chain was well mixed. And it's important for the chain to be well mixed for convergence. And for the autocorrelation plot, we also see that the dependencies of the realizations were in 10 iterates apart. So we see that on the lag, the axis, we see 0, 10, 20, 30, 40, and so on. And as the 10 iterates increased, there was an observed exponential decay, suggesting independence in the iterates. In other words, the observations that the estimates or the realizations we got from the MCMC were independent, and that is also a condition that we need that ought to be met for us to know that the MCMC had actually converged. Now, I tried to superimpose the estimates of INLA on the MCMC, and for the simple linear model, this is what we have. We see that the red outline constitutes the estimates of the INLA, and the histograms constitutes the estimates, all the realizations from MCMC, and we see that they overlap pretty well. Now, for the generalized linear model, we also had to do same, and overlapped very well. Now, as I've already discussed the convergence because of the trace plots, let me just move on to the accuracy. So we see that the estimates of tau, beta naught, and beta 1 were very equivalent when both estimates when the estimates from both techniques were compared. And then when we look at the time, we actually timed the processes, and MCMC for the simple linear model took 5.14 seconds to give us the realizations, and for the generalized linear model, it took 21.87 seconds to give us its realizations, but INLA in both instances took less than 3 seconds. And then when we look at the computational burden, we see that MCMC is more computationally intensive than INLA, because with MCMC you need to identify your prior, you need to identify your likelihood, determine your posterior distribution, and then deduce your full conditionals from which you will determine or estimate the parameters. And INLA was just a matter of identifying your response variable, your covariates, the data, and then applying the INLA function. So the significance and the conclusion of this work is that INLA outperformed MCMC in terms of the time of execution, because MCMC in both cases took less than 3 seconds, but INLA in both cases took less than 3 seconds, but MCMC for the simple linear model took more than 5 seconds, and then for the generalized linear model took more than 21 seconds. Now, when you talk about the accuracy, we saw from the table of values that they were very equivalent. They were not, there was no much difference between the estimates from both techniques. And then we also have seen that the MCMC was computationally burdensome compared to INLA. So our conclusion basically is that on the basis of accuracy, execution time, and computational intensity, INLA is a good Bayesian inference technique that can be used instead of MCMC when estimating parameters of simple and generalized linear models. Thank you.
Thank you, John, for that good presentation. I think you've taken a few more minutes over your allocated time.
Sorry.
We now invite comments and questions from the audience. Can raise your hand. Yes, Dr. Jerry Ochola.
Thank you, Prof. John.
So,
well, you've tried to make one good presentation here. But I was very interested when you started saying that you actually was trying to actually show that Markov chain or inlay is better than Markov chain. Monte Carlo Markov chain, of course, as you know,
not necessarily better. Let me correct, but it can be a good substitution, a good substitute approach to MCMC.
Sorry, John, I've not even said my question or comment.
Yeah, I'm just trying to let you know that the agenda was not to prove that inlay was better. It was just to show that it's a good substitution. That's all. But you can go ahead with the question.
John, allow Dr. Jerry to finish the question, then you'll respond.
Yeah.
Thank you, Prof, for protecting me. John, you should just have left to finish. So I was actually trying to say that, well, you've already, from your studies, Markov chain is a well-established approach, mathematical and statistical approach. So is INLA, by the way. So when the way you built your story and the way you actually concluded is that the only thing or the only area that INLA was becoming or having an edge over Markov chains was actually computational time. Okay. My question number one.
Yes.
What was the platform? Which platform did you use to run your computations or executions that you are talking about? And two.
Wait. Let him ask the second question.
For you to come up with the conclusion that MCMC took more time to execute than INLA, did you consider any other platform so that you actually compare two platforms to actually come up with this concept? Did you consider more than one platform to actually run your executions? John.
Jerry, you are through?
So,
yes, please.
Yeah, all at the introduction, I said that this study was carried out in R.
Okay.
So basically, everything was done in R. I have not tried any other platform.
Okay.
Yes.
Good. Thank you,
Prof. Before you go,
Prof, I think he's not done yet.
Okay.
Before you go, John, R is very old, and R, you should. They're actually much faster platforms that will actually give you a faster rate of execution than R. So when you talk about R, you will not have. Don't talk about the time of execution. Look for another parameter, because R, when you compare R and MATLAB or R and Python, you'll discover that maybe Markov chain could have done better in terms of time of execution. In my opinion, you should actually look for another platform if you want to have a better conclusion for your study.
Okay.
Thank you. But as far as I'm concerned, I know that R is a software for analyzing statistics, basically. So is MATLAB, so is all the other Python and all that. If you talk about it's old, I don't get that, because they keep giving us updated versions anyway. Besides that, it looks like your focus is more on the time, other than the values which were estimated, and the fact that they estimated the values, and then you did not even look at the computational burden of MCMC, because MCMC, you have to go through a vigorous computation before you can even run H&R.
Sorry,
because
John, can you go to your last slide? Can you just scroll to your last slide, the conclusion slide?
My laptop just froze, but
okay.
yeah, it just froze, so I'm not able to move. I would have moved a bit, but I think Godfrey has them. He can help us if he's able to.
No. Just to cut you short, I'm talking about the time, because that is the only thing you quoted that is the difference between the two. You actually said the accuracy was the same, the results were the same, but only the time that is. So that is why I'm quoting actually the time. But when you gave us any other parameter, I would have actually seen that even the other parameters, there was a difference between the two approaches. But the reason I'm saying R is actually old, I didn't meet old by age, so is MATLAB. But if you talk about computation of Markov chains, there are systems that run Markov chains under 5 seconds. That's what I'm telling you. So if R will do it in 5 seconds, Python will do it in microseconds, for example. That's actually what I'm trying to suggest to you. So can you try any other approach and see if INLA can still do it in less time than Markov chain? So I'm just trying to give you suggestions.
So that's
thank you, gentlemen.
But Prof, let me chip this in that as much as we're looking at the time, it also depends on the gravity of the data, because if you use data from spatial statistics, for instance, it's heavy. So definitely it will be time consuming, whether you use R or Python or whatever. So I appreciate your comments on the time, but all I'm trying to put across here is that besides the time, it is even computationally burdensome to use MCMC than INLA. So we can at the end of the day we can have estimates. That's fine, but how much work goes into arriving at the estimates we have? That's another thing we need to consider. The time, yes, but the computation are very intense in MCMC than in INLA. And whether you use Python or whatever platform, the intensity of the computation is not going to change. So that's the point I want to also add to the time that Doc is trying to bring across.
Thank you so much, gentlemen. I believe that the presentation now has generated the interest it deserves, and Dr. Jerry and Mr. John Dakwa will link up now for more clarifications. Yes. So as now science will gain. Thank you very much, John, for that nice presentation.
Thank you, Paul.
Thank you. Now we are supposed to have our next presenter. I'm not sure whether he's around. That is Juma Simiyu. Is he around? I've not seen him on the list of people present. Okay. That means that this presentation brings us to the end of our presentations this morning. And according to the program, I'm seeing we are supposed to have a poster session and then proceed for lunch break. And the time already passed. We were supposed to have gone at 13:10. And then we shall be coming back at 14:00 for keynote speakers. So at this juncture, therefore, I would request the Secretariat to take us into the poster session. But before that, I want to thank the presenters so much for giving us the new knowledge that they have presented to us, and urge you to continue being with us and attend the other sessions. I thank the ICT persons for enabling the presentations to take place up to where we have reached. And therefore, with that, thank you. I wish you good lunch for the remaining few minutes. Thank you.
Thank you, Prof.
The theme of this session is progressive textile. The presentations will include sustainable textile technologies, textile engineering, technical textiles and composites, textiles of the future. Welcome to Symposium 3. The theme of this session is progressive textile. The presentations will include sustainable textile technologies, textile engineering, technical textiles and composites, textiles of the future.